At the core of this project is a system that can be toggled on or off using a push button. Upon initialization, the system is inactive by default. As we enter the main loop, toggling the push button will change the system's state to the opposite value. Now, when the system is active, two LEDs come into play. We have a green LED, let's call it LED 1, and a red LED, which we'll refer to as LED 2. Let me demonstrate this by toggling the push button. The photoresistor is covered to ensure the alarm doesn't turn on as soon as the system is active. When the system is active, LED 1 is on and LED 2 is off. Conversely, when the system is inactive, the LEDs will swap their states, with LED 1 turning off and LED 2 turning on, and the alarm will turn off. This straightforward setup visually indicates the system's status. But wait, there's more. When the system is active, we introduce an additional condition using a photoresistor sensor module. This module detects the presence of light. If the system is active and the sensor module receives a low input, meaning there is light being received, and if the alarm is off, it will turn on. Let me demonstrate this by removing the cover off the photoresistor. Now, even if the photoresistor reads a high input, meaning that light is no longer received, nothing will happen, and the alarm will remain on. This is the key feature of this project, as it alerts us to a potential spontaneous breach of light. Now, let's focus on the alarm itself. When the alarm is on, a buzzer will beep periodically, alerting us to the presence of light. This continuous beeping will persist until we toggle the push button again, as I will do so now. This will cause the system to become inactive. This action turns off the alarm, ensuring it won't bother us anymore. This loop will be repeated countless times, allowing the project to be reused multiple times. In this part, we'll discuss the components used in our project and how they are wired together. First, let's talk about the photoresistor sensor module. This module offers several advantages over a normal photoresistor. It provides a digital input which makes it easier to work with compared to dealing with analog values. Additionally, the module features two LEDs. The LED on the right indicates whether the module is powered on, while the LED on the left turns on when the photoresistor detects light. Furthermore, the module includes a built-in potentiometer. By turning it clockwise, you can increase the sensitivity of the photoresistor, and by turning it counterclockwise, you can decrease the sensitivity. Next, we have the push button, which is connected to pin 10 as an input using a pull-down 10k ohm resistor. This configuration ensures that when the button is not pressed, it gives a low zero signal. This setup makes coding more convenient. The buzzer is connected to a PWM pin 11 as an output. PWM pins allow us to control the frequency and duration of the buzzer's beeping sound. We also have two LEDs, the green LED connected as an output at pin 9, and the red LED connected as an output at pin 8. These LEDs provide visual indicators of the system's status, with the green LED turning on when the system is active and the red LED turning on when the system is inactive. This project has a wide range of potential uses. Here are a couple of examples. Morning alarm system. For individuals who struggle to wake up with the sunrise to catch their morning run, this alarm system can be a perfect solution. By activating the system and setting it near a window, the alarm will beep as soon as light reaches the room, signaling the ideal time to wake up and start the day. Light prevention system. Imagine a scenario where you want to prevent light from reaching a specific area, such as a sensitive artwork or a plant that requires darkness. By activating the alarm system in that area, as soon as light reaches the designated spot, the alarm will be triggered, alerting you to take immediate action and prevent any potential harm caused by light exposure. These are just a few examples of how this versatile project can be utilized. With its customizable features and straightforward functionality, it can be adapted to various situations and settings where light monitoring and prevention are crucial. Now, let's take a closer look at the unique features that set this project apart from similar ones found on the internet. One of the standout features of our project is the ease of toggling the alarm system on or off. With the simple push of a button, we can switch the alarm state without any hassle. Unlike other projects found online, which often require unplugging the device or covering the photoresistor to turn off the alarm, our project offers a convenient and user-friendly solution. Once the alarm is activated and the photoresistor detects light, the buzzer will start beeping. Here's where our project distinguishes itself from others you might find on the internet. In our project, regardless of whether light is still being detected by the photoresistor or not, the buzzer will continue to beep. This realistic feature prevents any irregular action from prematurely turning off the alarm. Unlike similar projects online that only make the alarm beep as long as the photoresistor detects light, our project ensures a reliable and consistent alarm function. Our project offers a practical and effective alarm system. With easy push-button toggling and realistic light detection behavior, it's a valuable addition to any security or monitoring setup. In this final part of the video, let's delve into the detailed control flow of our project and how it relates to the code you provided. Understanding the control flow will provide a comprehensive understanding of how the different components work together to achieve the desired functionality. The control flow of our project revolves around the state of the system, which is determined by the push button. Let's examine the control flow step by step, linking it to the provided code. Initialization. The project starts with the initialization phase, where the system value variable is set to false, indicating an inactive state. Other variables such as button state, LED states, and alarm state are also initialized accordingly. Main loop. The code enters the main loop, which runs continuously, checking for changes in the button state and the photoresistor sensor value. Button toggling. The code checks if there is a change in the button state. If the button is released after being pressed, low, and the current button state is different from the previous state, the system value is toggled by using the NOT operator. This toggling changes the system state from active to inactive or vice versa. LED control. Based on the system value, the code controls the state of the LEDs. When the system is active, system value true, the green LED, LED 1, is turned on by setting the corresponding pin to high, while the red LED, LED 2, is turned off by setting its pin to low. Conversely, when the system is inactive, system value false, the green LED is turned off, and the red LED is turned on. Alarm activation. If the system is active, system value true, and the photoresistor sensor value is low, indicating light being received, the code checks if the alarm is already on. If the alarm is not active, alarm on false, the alarm on variable is set to true, indicating the activation of the alarm. Alarm beeping. If the alarm on variable is true, the code enters the alarm beeping phase. The buzzer pin is set to produce a tone with a frequency of 2000 Hz using the tone function, creating the beeping sound. The buzzer remains on for 200 milliseconds, ms, then turns off using the no tone function, creating a pause between beeps. This beeping and pausing cycle continues until the push button is toggled again, turning off the system and resetting the alarm on variable to false. Button state storage. To keep track of the button state changes, the current button state is stored in the last button state variable for comparison in the next iteration of the loop. The code, documentation, and Fritzing schematic are all provided in the description to assist you in better understanding the project, particularly if you encounter difficulties while working on it independently. By understanding the detailed control flow of our project and its connection to the provided code, you have gained insights into how the different components interact and function together. This understanding allows you to modify and enhance the project according to your specific requirements or explore additional functionalities.